quantum operators can actually be expressed in any coordinate system that's handy to describe a certain system. And so you can choose one that will simplify the mathematical form of the quantum operator, or otherwise somehow is suitable for the system in question. So I'll remind you that for the particle in a ring model, we did start actually with a Hamiltonian that looks something like this, and it had second derivatives with respect to x and y, but these were not very convenient because we had to specify that r was held constant. So instead what we did was we used plane polar coordinates to re-express this Hamiltonian, and we were able to do that in terms of a much better Hamiltonian that looks something like this. All right, much simpler than the form that we had in Cartesian coordinates. Well, for these purposes, the spherical polar coordinate system is actually going to turn out to be a very handy system for us to use for a number of different systems, in particular when we start talking about atoms. And so that's why I want to introduce it here. Now, I'll remind you that the spherical polar coordinate system is defined mathematically as follows. The x-coordinate is equal to the distance of the point from the origin. So here is the point over here, and the distance from the origin is r times sine of theta cosine of phi, and y would be r sine of theta sine of phi, and z would be r cosine theta. So how are these angles defined? Let me indicate that. All right, so first of all, the distance here is r. So that is our length parameter in the spherical polar coordinate system. The angle that r makes with the z-axis is theta. And so that helps us define that. Now, I'll note that if we were to draw a horizontal line from the z-axis out to this point, and then drop a line straight down to the xy plane, that the angle here is now the angle phi. So we can see that by defining r as the length here, theta as the angle with z, and phi here, this is the set of transformations that we would have. So now we can write this point, instead of being x, y, z, it's r theta phi, and they both define the same point. Now I'll note that r runs from 0 to infinity, and theta runs from 0 to pi. In other words, it just goes down to the negative z-axis. And phi runs from 0 to 2 pi. By defining these parameters this way, we guarantee that every point in 3 dimensions that can be given an x, y, z coordinate has only a single r theta phi coordinate to go with it also. All right, so that's one reason we do that. Now, another thing that we would get from this coordinate system is it changes our volume element. So, for example, the volume element in x, y, and z space is dx, dy, dz. So if we were doing a triple integral, this would be the volume element for that integral. When we transform to spherical polar coordinates, it actually is a little bit more complicated. It ends up being r squared sine theta dr d theta d phi. So in x, y, and z coordinates, we would have 3 integrals that would all run from minus infinity to infinity. But when we go to spherical polar coordinates, we'll have one integral that goes from 0 to 2 pi, d phi. We'll have another integral that goes from 0 to pi, that's d theta, and it has an element sine theta. And we'll finally have an element that goes from 0 to infinity, dr, with a weighting of r squared. So now a triple integral that was simple to write down in Cartesian coordinates becomes a little bit more challenging to write down in spherical polar coordinates. It's also important that we change our differentials. So this is similar to what we did in the case of the particle in a ring system. If we have a differential with respect to x, we need to write that in terms of differentials in r, theta, and phi. So in other words, we would have a chain rule type thing we'd need to work out, where we're evaluating dr dx ddr, and then we're adding d theta dx. This is at constant r and phi, and that would be d theta. and we would have a term that would be d phi dx, that constant r and theta, d phi. So we would have to determine these partial derivatives for all of the coordinate pairs that go along here. I'm not going to drag you through that exercise, but I will tell you that it's helpful to know that we can write r as the square root of x squared plus y squared plus z squared. We can write theta as the inverse cosine of z over r, or inverse cosine of the square, cosine of, what am I doing? Z divided by square root of x squared plus y squared plus z squared. And finally, phi would be the inverse tangent of y over x. All right, so those things would help you with that. Okay, but since we're not going to go through the whole operation of doing these partial derivatives, let me just give you a few important results from doing this. Okay, first of all, when we're writing a Hamiltonian for a system in 3 dimensions, we might start with an expression that looks something like this. We'd have Hamiltonian is minus h bar squared over 2m times the sum of 3 squared, 3 second-order derivatives in x, y, and z. And I can tell you that this is going to be true for every Hamiltonian in 3 dimensions. And we may have a potential that also depends on x, y, and z. All right, but this particular combination of things is very, very common. So in fact, what tends to happen is we define a special operator that is, if you will, it's the vector of these 3 partial derivatives. So it's a vector operator that contains the derivatives as its components. And moreover, we define the square of this as 2 successive operations, a dot product between these 2 vectors, so that we get d squared dx squared plus d squared dy squared plus d squared dz squared. All right, this operator occurs so commonly it has a name. It's called the Laplacian. And it's often this operator that we want to express in different coordinate systems. Okay, so the good news for you is that in many quantum mechanics classes, people are given an exercise for transforming to spherical polar coordinates and write the Laplacian in spherical polar coordinates. Well, I can tell you this is a very tedious and lengthy exercise in algebra, so I'm going to give you the answer. And here it is. The Laplacian in spherical polar coordinates is given as follows. 1 over r squared ddr, r squared ddr. You'll notice there's this interesting way of writing this where we've got the coordinate and the derivative with respect to the coordinate. It just turns out that this is a more compact way to write this expression. All right, we also have a term that looks like this. 1 over r squared sine theta dd theta times sine of theta dd theta. And then finally we have a term that's 1 over r squared sine squared theta times the second derivative with respect to phi. So this is our expression for the Laplacian in spherical polar coordinates. And we're going to be making some use of this expression in the next few lessons, especially as we start talking about atoms, where this one's going to come in very important.